handouts, so if you need an extra copy, I got those for you as well.
I don't want to pour out.
Like 500 people in it, where is it?
Yeah. Alright, so first one, iron 2, or iron 3 sulfate. Let's go ahead and balance that. If you're looking, all sulfates are soluble. Commit your ACS to final exam, they actually don't give you solubility rules. So you have to memorize them. Ish meaning I would learn the major ones, like all nitrates are soluble, all alkali metals are soluble. Any of the heavy metals, lead, mercury, those sorts of things are typically insoluble, right? And then learning some of those other insoluble components like carbonates and hydroxides typically are, you have a reasonable guess on most of those. So there's way too many to memorize all of them, so just choose the major categories and classifications. All right, so if I gave you the name iron 3 sulfate, that means this is a positive 3, and sulfate applies a polyatomic ion negative 2. So to balance that, we'll come back to that. Let's go ahead and predict the products of the reaction first. So notice I put in here that we need at least one solid to form. It doesn't matter what the compound is, as long as it's a solid and it doesn't violate the conservation of matter. So we have to have the same number of atoms on both sides. So we need to choose, in essence, a cation that either reacts to form a solid compound with sulfate, or we need to form an anion that reacts with iron to form a solid compound. So you choose, doesn't matter to me, but we have to have that scenario. So look at your sheet, choose something that's insoluble with lead or iron, or insoluble with sulfate. What do you want?
You said insoluble,
Insoluble.
with iron and insoluble with?
It's one or the other, so either insoluble with iron or insoluble with sulfate.
Silver.
Silver sulfate?
Sure.
Yep, okay. So silver sulfate, Ag plus SO4, is insoluble. We'll come back and balance again. That means over here we have to have the silver ion there, right? And whenever we're doing double displacement reactions, a requirement, so I don't remember if I wrote this or not. If I didn't, I should have. A requirement is that these two reactants have to be aqueous. That is the requirement for double displacement reactions. It doesn't matter what products you form, what phase states, but the requirement is those are aqueous. So now we need something that's aqueous with silver.
How do you know if it's aqueous with silver?
Yeah, you find the silver ion, and then silver can or has to be either the exception on the insoluble table, or it has to be soluble on the soluble portion of the table.
Yeah, I think I'm lost on this little table. Don't
Yeah.
you have this?
Hey, this one is great, by the way.
That's a pretty extensive one, yeah.
It's not
Yeah.
making sense.
Chlorine, silver chloride?
Solid. You just find one.
Does that work?
That's an
Yeah.
exception,
Do you
that's
need
insoluble.
What about chlorate? Pretty self-explanatory.
Chlorates, yep, we can do chlorate, that's fine. All right, now here's the check though. If we do silver chlorate, iron chlorate's going to be formed. Is iron chlorate soluble?
Yeah.
Yeah, because there's no exceptions to the chlorate. So all chlorates are soluble all the time, no exceptions, right? That's especially with the nitrates in there as well. So this is fine. We don't have to have aqueous here. We could have formed a solid, a liquid, or gas. It just worked out in this example. We wanted an aqueous, and it's fine. Okay. All right. Now let's try to. It's double displacement. Let's try to balance the molecular equation. So for the rest of the year, after this chapter, you will not have to do all this stuff. That's with it. But let's just try to kind of go step by step, just to kind of jog or refresh your memory. I think based on what I've heard you guys say about other reactions, you actually have a pretty good foundational knowledge. So let's do this. Total ionic equation, and then we'll do a net ionic equation as well that are with there. So this currently is unbalanced. Okay, all right. 2 steps. Whenever you're balancing chemical equations, you have to balance the oxidation states first. So step 1, oxidation states. And when you do that, you have to use subscripts. Okay. After you balance the oxidation states, and only after that, so there's it'd be very difficult, near impossible, other than a guess, you would use the coefficients to balance mass. coefficients. So conservation of matter and energy says you can't create or destroy matter or energy. You can only transfer it from one system to another or transform it from one type to another. So if iron shows up on the left side, the reactants, it has to show up on the product side. If it shows up twice, it has to show up twice. The type of bonding is different though, right? John Dalton, remember as we were discussing, the scientists back in the 1700s said, element A is element A, element B is element B. A and B are not the same thing. A and B can mix, or A and B can combine to form a compound. And how they do that is based on percent compositions. You always have 2 parts hydrogen, for example, to every 1 part oxygen, whenever water is formed. However, in a different scenario, you could have 1 part oxygen and 1 part hydrogen whenever you have the hydroxide ion formed there. And you could just keep extending that combination to, well, maybe you have 3 parts hydrogen to 1 part oxygen. What happened? Me?
We have a ghost.
No, that's just the imbalance of the temperature pressure in here.
No, we have a ghost.
Oh, okay. But this is John Dalton, right? That's in essence what he's saying. So looking at the ratios. All right, let's balance the subscripts first. You can do this in your head if you want to. I'll just show you one method. That way, if it doesn't work out in your head, you can always come back to this as a default. So in general, here's what we say. If there's no charge out here to the right side, that's where the charge would be noted, then that is an electrically neutral species. So we're going to put a 0 here. This is the individual oxidation state of iron and the individual oxidation state of sulfate. Sulfate is a -2 charge based on its position on the periodic table, the periodic trends that we're using, or if you just memorize it. The oxidation state of iron is a +3, and I would have to tell you that. I'd have to say the name iron 3 sulfate reacts with, and then you can know the oxidation state. Since iron is a transition metal, it could have multiple oxidation states, and that's why the name is important. 3 plus -2 is definitely not 0, so finding a common multiple of 3 and 2 is 6. That means we need 2 irons, and we need, parentheses, 3 sulfates. So you don't have to do this. If you want to do this in your head, great. You never have to show me this oxidation state work. I will know what you're doing, because if your subscript is correct, you've done the math appropriately. Fair? So this is the oxidation states are balanced. Notice there's a slight shortcut. A lot of teachers like to present it. I think it works 75–80% of the time. Whatever the oxidation state of one is the subscript of the other. Whatever the oxidation state is the subscript of the other. That's a quick little general gauge, and then double check the math after that. Yeah.
How do you know if it's the other 20 to 25%?
What I mean by that is the individual oxidation states of sulfur and oxygen. What's the oxidation state of oxygen? -2, and sulfur?
+6.
+6. So what we really should have written is iron plus sulfur plus oxygen equals 0,
Oh.
where this is 6, 3, like this. And then in terms of how many of those, we still would have 2 irons. How many sulfurs would we have? 3. And how many oxygens? 12. And that would come out to be 0. So if in that crisscross situation, it's like, oh, this 6 goes with this, and you're like, wait, what? You see? That 6 is not the 4, and the 2 is not the 1. So there's the other 20% of the time, is really when you're dealing with polyatomic ions or charges. So the crisscross method is a good just initial guess, then double check the math ultimately. That's with there. Okay, so let's not necessarily do the long route. Let's try to maybe do it a little more quickly. Oxidation state of silver, always +1. What's cadmium? Cd.
Oh, wait, let me look.
Cadmium.
2,
2, zinc,
2,
and aluminum.
3.
Good. So those are must situations.
2, 2, 1.
What is the perchlorate ion's charge? Perchlorate.
-1.
How do you know?
Because it's 1 from the...
Yeah, the 8 form is O3, perchlorate is O4, but chlorine is 1 position away from a noble gas, therefore its charge as a polyatomic ion is -1. So we don't have to memorize that, we just need to apply the general pattern. Whatever the oxidation state of iron is here isn't necessarily the same oxidation state of iron on the other side. Remember, that deals with this question of redox. Gen Chem is also going to go through these. They're not covering these at all in depth, like legitimately, they just need to know, basically, like, heat's produced, that's it, yay, you know, that sort of thing. So, redox for you guys, though, in any reaction could occur. The oxidation state of iron might actually now be a positive too, and we could balance that way. So how do you know? Here's what you're going to do. You're going to make the assumption the oxidation state does not change unless I tell you it does. So I would have to give you the name iron 2 chlorate is formed instead of iron 3 chlorate. Otherwise, make the assumption it's positive 3. All right, chlorate's a -1, so that means we need 3 of these, 3 different -1 charges, balance out the 1 positive 3 charge. Sulfate's a -2, so we need 2 different positive 1 charges. Now, notice that takes care of step 1, right? We've balanced all the individual charges or oxidation states of every atom in the compound. Now we are able to do step 2. If you didn't do this first and you tried to do this, we would have had equal number of iron to begin with. We never would have needed to put a subscript there, equal numbers of chlorates and silvers and sulfates, and it looks like it would have been balanced, but it wouldn't, right? The ratios would be totally off. Okay, now let's go ahead and balance it. Again, you don't have to go, this I haven't done yet, but you don't have to go through all these steps. This is just a general idea here. So if these elements show up on the reactants, they also have to show up on the products as well. A lot of times I try to keep the polyatomic ions together. If we balance the number of chlorines, is that the same thing as balancing the number of chlorates?
No.
Let me think about that. Does chlorine show up anywhere else
Yeah.
other than in the polyatomic ion chlorate?
No.
Okay, so if we balance chlorate, we balance the chlorines. Fair?
Yeah.
Right? So it's also just helpful to categorize things that way. All right, we have 2 moles, so I'm gonna use the right, if you will, terminology with you guys. Again, Jim Kim, I would say there's 2 things. There are 2 moles of iron there that are present. That means for every 1 mole of this compound, we have 2 moles of iron present in that compound, right? Twice as much amount of iron there, okay? So 2 moles of iron, we have 3 moles of sulfate, we have 1 mole of silver, so that's the subscript of 1 implied, and 1 mole of chlorate additionally. Over here, same thing, we have 1, chlorates we have 3, silver we have 2, and sulfate we have 1. So we're using the subscripts to get these numbers. Now those just tell us how much is currently present. Now we have to actually end up balancing it. Notice that iron is not the same thing. The easiest method is to multiply by 2. Whenever you do that, this now becomes the coefficient right here. So I need 2 moles of iron. If I put a 2 there, that gives me 2 times 3 moles of chlorate. So that means I just multiplied this by 2. So that's 6. If I have 1 mole of chlorate here, I need to have a 6 here. If I do that, that gives me 6 moles of silver. I'm just drawing arrows so you know where these numbers are coming from. And now what?
You gotta put the 3 in front of the silver
Okay.
sulfate.
If I put a 3 here, this 3 is for sulfur, or sulfate rather, and 3 times 2 is 6, right?
It works.
So it works out nicely. So again, you do not have to do all of this grid multiplication arrow thing. Actually, I would encourage you to move away from that. It's a lot of work, it's a good check, but if you can get yourself away from that, you'll save a lot of time. So this is just kind of the first round to see what numbers are actually lining up. Okay, so that's step 2. Now we have a balanced molecular equation, not unbalanced officially now. And arguably for the rest of the year, we don't necessarily need the balanced equation unless we're doing math. If we're doing math, we need the balanced equation because of mole bridges, etc. If it's just a generic statement, like showing the demos and stuff yesterday, we really didn't care how much of what reacted. Maybe for the hydrogen and oxygen, we did to decide which terminal was producing what kind of gas. But otherwise, we don't officially have to. Okay, so let's let's move into now the total ionic equation. The total ionic equation is this. If you can form an ion, write it as an ion. Okay, so what we're saying there is looking at phase states. Just as a side note here, this Fe2SO4. Okay. If that's aqueous, that is the same thing as drawing a picture of a beaker, putting pure water in there of some amount, we don't know how much, taking a solid chunk of the iron 2 sulfate, so that would have been a solid, dumping it into here, letting it dissolve to every extent. Every time one of these dissolves, we get the iron 3 ion, but twice, right? So there's Fe3 plus, there's Fe3 plus, and every time this compound dissolves, we get 3 different sulfates. So SO4 2 minus, I'll just put one here and one here, right? So this is the same representation as this symbol. So you can see why more tedious, kind of takes up a ton of time versus much significantly better. So these are actually written as the real ions, Fe3 plus, and we have to write that as SO4 3 minus. Okay?
So they,
Isn't it 2 minus?
Oh, sorry, 2 minus. Yes.
Right?
and they separate?
And they are separate. Yep. Anytime you see a Q, those ions are not together. Now, I guess I should clarify that. If this is a positive charge species, right, and this is a negative charge species, okay. If you want to write it, you can. If you don't, that's fine. Let me
Do
clarify.
we need to write it?
No, because it's more of a conceptual idea, just to show.
Alright.
The big picture.
Oh, what is that?
So you have your water in there. Okay. All right. At some point, will these two ions collide and interact? Okay. They will interact because they're opposite charges, and they will collide because they're in the same beaker together. They actually collide about 1,000,000 times a second, legitimately 1,000,000 times a second, so very fast. Now, will they stay together?
No,
Why not?
because of the H2O.
What do you keep going? What do you mean by that?
There's other ions and charges that we separate.
Keep going. You're all saying you're saying the right things. Just keep going.
It also collides with other things.
Yeah, there you go. So we have a couple options. We did present this way back in the day. It might have been a while, so we definitely probably need a little bit of a refresher. So remember how water orients itself around these positive charges? Why is water's oxygen orienting itself around silver?
Because oxygen is polar.
Okay, oxygen is slightly negative, and the negative is attracted to the positive portion. So how will water orient itself around the chlorates?
Oxygen.
The opposite, right? So just I'll draw a couple, so we don't have to draw all of them. But the hydrogens are gonna more orient themselves around there, the negative charges. That's called solvation or hydration. So how does water orient itself around charged species? If you guys were looking for the word there, this would be an ion-dipole interaction. Remember when we were talking about intermolecular forces, the dipole of oxygen interacts with the ion of silver. If this interaction is very stable, what will happen to this interaction? So if these interactions are stable, and these interactions are
It
stable,
will be stable.
this will begin
It won't
to weaken.
attract.
And if that weakens, now, in terms of a phase state, you say silver ion and chlorate ion are dissolved, or soluble in water, and you call that aqueous, actually separated apart, right? Now, why does water not show up? Why do we not say, oh, this and water?
Because aqueous tells you it's
Yeah.
water.
This aqueous symbol means water is in excess. There's so much of it that it's just implied. It's there. It's so big, quantity amount. Now, what is of concern and of interest in the chemical reaction is the species that's actually being dissolved in there, not actually the water itself. So this is the process of solvation and hydration. Now, keep playing that out. Go back to something Jolyn just said. There's other ions in there additionally. So if let's just pretend this one's also surrounded by the oxygens of water, right? I'll just draw the oxygen components, maybe the hydrogen components of water around here like this. Will this iron ion ever collide with the silver ion? In a solution, will they collide?
Yes.
Yes. Like picture 4 colored marbles in a bucket, a 5-gallon bucket where there's a million of them, and just start shaking them. At some point, will the red marble hit the blue marble? Absolutely. Is that a stable interaction?
No.
Why not?
Because it's already stable within its own
Keep going.
bubble.
True.
and so-
What else matters there?
They're both cations.
They're both cations, repulsive in nature. So as they start to come together, like no, 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 yes, 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 right? And that goes back to your energy grid that we've been drawing multiple times. This one, where take two opposite charges, a positive and negative charge, begin to separate them infinitely far apart. Takes a lot of energy to do that, or drag them very close together. What's the ideal distance? That's great. Now do that same thing for positive charges and say like, whoa, 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 we don't want to, yeah, you know what I mean? Like that conversation still continues there. So if these two collide, will these two collide?
Yes.
Stable?
No.
No. Will these two collide?
Yeah.
Yes. So that's what we're looking at in double displacement reactions is what are the possible collisions? A and B could collide, C and D could collide, A and C could collide, not stable. B and D could collide, not stable, 2 anions. A and D could collide, perfect. And C and B could collide, perfect. So we're writing the different possible stable configurations of cation and anion interactions. Yeah.
So it doesn't matter which one is more stable, the left compounds or the right compounds? Like are they
In
equally-
terms
are
of
they
reactants or
equally
products.
stable?
Say that one more time.
Are they equally stable?
No.
Or is
Yeah.
So what's the difference?
Yeah, so if we want to say, will this reaction occur, we have to form a solid. Will the reaction, if the reaction doesn't occur, then if we wrote this as aqueous, what would that mean?
But they're going back and forth.
Yeah, it literally just means you have all ions still in solution. Nothing's come together. Everything's still floating around, right? So the reaction doesn't even exist. You just mix two things together and nothing happened. Yay. You know what I mean? Like that's not a good situation. So we want a solid to be formed if we want a reaction to occur. So what I would do on your solubility table, on the exceptions where my finger's at under the soluble, those exceptions are insoluble, and you would say reaction occurs. Insoluble reaction occurs. Down here on these exceptions, that's no reaction because it's soluble. So down on the second exceptions, those are soluble, no reaction. So anytime we say insoluble, we're going to correlate that to a reaction did occur versus the soluble species. Now here's the cool part, and again, this is akin to concept because you guys have seen enthalpy before. Think of this equation. I'm not going to tell you necessarily what it is right away. I want to see if you can get there. If I put delta H of something, let me put question mark here. Okay, and I guess I'll go ahead and put overall to help out. Look at this, solute, solvent, solvent. I haven't defined those words for you. Take a guess. What's the difference between the word solute and solvent?
There's a U and a V.
Oh, that's true.
Yeah.
What are they in terms of the sign?
Solute is what gets dissolved in the solvent. right?
Okay, perfect. This is the thing being dissolved. And I'll put thing because it could be a lot of stuff.
Wait, solute is the thing being dissolved?
Yeah.
Okay, yeah, yeah.
And the
So
solvent
that's the whole thing.
does the dissolving. And in terms of that, what we mean by that is water.
The universal solvent.
Yeah, the universal solvent. And the key there, to your point, is likes dissolve likes.
What?
Yeah. So things that are polar dissolve polar, things that are non-polar dissolve non-polar, right? That's the whole basis of the phospholipid membrane in biology. The fact that you have a phosphate group with hydrophobic tails that orient themselves inward away from the intercellular components that are watery in nature is a very good thing. Otherwise your cell would break down, right? Okay, what's going on here? I didn't tell you, so try to describe this. In terms of this image, this is the heat, the energy, the enthalpy associated with solute and solute.
Solute 1 and solute 2.
Okay, so if these two iron sulfates are actually together initially, So if you really did have a solid and then you took that solid and dumped it into here, this is the energy needed to actually break those two ions apart. Notice we have a diagram that helps us understand that. In addition to that, you have your bond enthalpy. You don't actually have it on that list, that table. There's nothing on there that says take iron and sulfate and break that bond, that interaction, but we could calculate it. Is this going to be endothermic or exothermic? To break bonds,
Endo.
that's endo, always, 100% of the time, no exceptions, right? We won't go back in to talk about it, but remember your potential energy curves. If, which one is endothermic overall?
Endothermic is bottom.
Bottom, so this is delta H, this is positive. And this is delta H here, that's negative. And if that's the case, we're looking from this point to here, and this point to here, right? You always need energy to begin to break those bonds. That's an endothermic idea. What about here? This would be water interacting with water. What types of intermolecular forces, IMFs, intermolecular forces, does water have?
Hydrogen.
It has hydrogen bond, what else?
Ion dipole, right?
That's fair, but not to an appreciable extent. I never told you guys this, but water, and you don't need to know it, but water will self-ionize to form these ions in solution. So water is slightly acidic. This is, if you take Chem 3, you need to tell your parents you want a Chem 3 class. They have the leverage.
Yeah, tell me
They
about it.
have the leverage.
I literally
They
am going
can.
to a whole different school, so
That's
I
what I'm
can
saying.
take
You
Chem
need
3.
to tell your parents and talk to admin. I'm serious about that. They would. I have no leverage. I put in
I
a
feel like by the
proposal,
time it would get passed,
wrote
we
up the
would
curriculum,
all be
sent the
graduated.
syllabus,
We'd
said
all-
let's do
yeah,
it.
we'd all
All of us would be
And
graduated
they're
by the
like,
time that class even existed.
No, next year.
We
could
already
get it
signed up
passed
for our
next year.
classes.
We already
The-
signed up for those.
The curriculum's ready. The syllabus is in. It's sent. It's
Really?
up. I'm ready to go. I'm itching.
You really have like
I'm
a.
itching.
Wait, what if they gave it to another teacher to teach?
Oh.
I mean, they could.
So then would you just be
But would you be sad? Like you went through.
I'd be sad, but I'd still be happy we got a Chem 3 class.
But you
I feel like we don't have enough teachers to do that because we're losing
I
like
don't
3
have
of
the
our.
full-
You know how many schools don't even have a Chem 2 class?
I know. We need a Chem 3 bad, though.
Why?
Goddard's got almost 30 people on Chem 3. 30.
They wouldn't let me take you
But
over
the
there.
thing is
That's crazy.
people can only take Chem 3 if they stay in Chem 2, and we're
That's
only
true.
people taking
That's true.
Well, I mean,
But
we also
and last
have-
semester.
Well, we've got like a lot of.
Did you only have one class
Yeah.
last semester?
What's that?
Did you only have one class last
Yeah.
semester?
4, 5, 6, 7.
Yeah.
Wait, 1,
Yeah,
2,
we
3,
need
4,
Chem 3
5,
bad.
6,
We don't
7,
even have
I'm
enough
so
people taking Chem 2.
anxious. I'm so anxious for
Because
it.
together that'd be like maybe
Morgan,
30
you
people
don't start
for
with
one
me.
class.
signed up.
If
Yeah,
every
we're
single
back.
person
We're-
signed up, which
Well,
I'm
no,
pretty
no,
sure
because
most
there's
of us
last
aren't.
semester Chem
I
2
wouldn't.
students.
It's worth it.
Oh, you're right.
Trevor, would you
Anyways,
sign up for a
um,
Chem 3?
Minimum.
You don't
That
have
sounds so
you don't have to know this, but
I feel like we do
in
more
like a Chem 3
experiments
course,
or research.
and it actually would benefit you a lot if we did study acid-base chemistry. We've talked about that, but there's a way to talk about these concentrations and correlate that to a value. It's called an ion product constant for water. How does that relate? We don't need to get into it, but eventually, blah 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 blah, it turns into the pH scale for us, and then it provides a calculation to be like, oh, what's the actual concentration of these ions in water? So we could literally take water out of the tap, put a pH probe in there, measure the pH value, correlate it to a hydrogen ion concentration, and tell specifically how much water has dissociated randomly, uninfluenced by us, to these respective ions. So to your point, are there ions in water? Yes, here they are. To what degree? Very, very little. But they're actually there, present. You can figure all that. Okay.
Anyway, that was a really
Yeah.
good saying there's no ion. That was legitimate.
What else? What else?
Dipole?
Keep going. Anything else?
London dispersion.
Ah, use the word. Why'd you say London dispersion?
Because it's London, and I remembered it was like part of the country, and then I remembered
Oh.
that was also part of the
So,
bonds.
instantaneous and induced dipoles. Okay, my reason is showing you, because that's 2 here. 2 of these, this would have 1, this would have 1. And, well, in terms of different types of bonds. The hydrogen bonds actually come out to be 4 of them. We could take water's head, right? Remember, we could interact with here, 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 and here, off the sides. you're breaking 1, 2, 3, 4, 5, 6, 7 different types of bonds. That absolutely has to be a very endothermic process. So how, in your phase diagram, ooh, remember that thing? Remember this thing? Remember that thing?
I'll
Solid,
scream it.
liquid,
It's like-
oh.
This was,
Yeah.
that was the big
It's the easiest part.
You did it, remember? We did it.
Yeah, it wasn't actually difficult. I don't know why we all like.
Which portion of the curve are you on if you're breaking the solvent-solvent bonds? Are you here or are you here?
You're horizontal.
So
If
which
you're
part?
breaking, yeah,
You're
So-
breaking when you're
So what I'm asking you
horizontal.
is potential or
Potential. That would have
kinetic?
been a better way to describe that than just horizontal.
Yeah, but potential is correlated to breaking bonds. Kinetic energy is about speeding things up. Fair? Wow, candy? No.
Dude, I wish.
That's
Paper?
you push it just for me. Oh,
Does
no
it say
candy.
we have come three?
What's that?
Does it say we have come three?
No, it's my sub list for Stricker today. I'm selling for Stricker. Do I have you?
Wait, is
6
it left?
hour?
Oh, no.
Oh,
I have a next
Wait,
block.
wait.
6 hour?
What are you? Wait, what?
I
What are
don't
you
know.
doing in
I'm
that
just
class?
subbing. I don't know yet. I just show up and say hi.
Are you
That's all I
breaking
do.
that class down here?
Probably. I don't know. All right, but potential energy breaking the bond. So this is kinetic. How do we know that? Because our temperature is changing. So that's the degree of the measure of the motion. So if we're breaking bonds, we're somewhere in here or we're somewhere in here. So what you're looking at in terms of this statement is what is the delta H of? What do you call that? Delta H of going this direction? Solid to liquid?
Fusion.
Fusion.
Oh, okay, boy. That took us way too long.
And
Delta
delta
H melting.
I don't have access.
I mean freezing.
solidification.
Yeah, freezing.
Delta H vaporization, delta H condensation. So you're looking at those values, experimentally to determine values. Okay. Now, what about this one, endo or exothermic? Think very carefully, not a trick question, but think carefully about that one.
What?
The last one, delta H solute solvent. Solute solvent. Taking a solute and binding it to a solvent.
I think it's gonna be exothermic.
It's exo, because bonds are forming.
Yes, perfect. I love
Let's
that
go.
response. So that's exo. And the rest is endo. So overall, to Jason's question originally, which is, will this reaction occur? That's a thermodynamic question, which means it's dictated by energy. If the energy is lower in the products than in the reactants, then the reaction will proceed energetically most favorable direction. The ions will assimilate themselves to create a new arrangement of products. If you have to put energy into the system to make the reaction occur, that means this is positive overall. Could you still have a reaction? Yes, but what?
You'd have to have.
You have to add some energy, heat it up, or add ultraviolet light, something to make that reaction go, because it's not energetically favorable. When will this be negative?
If the exothermic is more than both.
Yeah. If the stability of these interactions, oxygen and the ions, or the hydrogens and the ions, are more stable than any of these interactions, right? Then you will have a very exothermic result here, typically. Not always, but typically. Kind of cool to see how your enthalpy kind of progresses even into chemical equations.
Do we have to memorize that?
Which part?
The enthalpy thing.
April 14th, the day before you guys leave for your 4-day weekend. I already got it ready to go. I'm going to give you a thermochemistry review. This is chapter 5, what you guys actually already did. It's just in the enthalpy stuff again, and this will show up on that.
What day?
14th
Oh, wait, no, yeah, we do have state testing that day.
on a Thursday.
Ew.
Yeah.
Oh, you're right. So maybe I give it to you Tuesday.
Why does that indicate that you do two?
Because I may not see you, right? On
Morgan,
Wednesday,
you just
Thursday?
No,
want
no,
to
no,
it's just Thursday.
Some of us do it first and second block, and some of us do it third and fourth block.
But not on Wednesday?
No, it's all
It's all
Thursday.
Oh, I'll get
Do we
you
just have to
Wednesday.
go to our regular
Because otherwise I
classes?
won't see some of you, right?
Do you have
Yeah,
the first
because
or
I
second?
want-
We just have to go to our regular classes or?
First and
Oh,
second.
yeah.
I'm pretty sure we have it.
Cool.
All right, total
Would you
ion.
still go to your, like,
Okay,
We're not
That
doing,
works.
we haven't done total ion.
The original question is how do you figure out whether those are going to be ions? This is how you figure out whether those are going to be ions. So fortunately, if this is aqueous, just looking at the solubility table is sufficient. You don't have to necessarily go through this full process of enthalpy calculations to determine whether they're going to be ions. They will be because the science data is there. That's the solubility table. All right, so write them as ions. We have the iron 3 ion. We do need to include the phase state there. So it's still in a solution of water. The sulfate ion is also still in a solution of water as well. How many of each of those do we have though? How many of these ions do we have in this formula?
2 iron and 3.
Okay, so watch very carefully. The 2 goes here because that says 2 different ions. That would be like Fe3 plus and Fe3 plus. If we take that 2 and put it here, what does that mean? It still means you have 2 irons.
But it's in a single compound.
It means that it's in a single complex or bond. It's like they're somehow interacting together. And it's like, well, really? You know, like be careful with that. So I would say easily that's the most overlooked portion of this kind of introduction is that subscript 2. All right, now sulfate, we have 3 of those, right? We can write the silver ion because this whole thing is aqueous, so silver ion still shows up in solution. There are 6 of those. We have 6 chlorates as well that are still in solution. So if you had to say, draw this for that reaction, it's just you have the iron, you would have the sulfates, you'd have the silvers and chlorates, and you draw all the hydrogen surrounding and the oxygen surrounding the respective ions. Okay, now do the same thing here. We have the iron 3 ion. It's in solution. How many of those do we have? 2. 2 moles of those.
Since we already balanced it, it's just gonna be the same
Yep.
thing, right?
And then we also have 2 chlorates times 3. So let's be careful with that. So there's chlorate. In one of these compounds, you have 3 of them, but you have 2 moles of that compound. So there's 6 of those. Fair? And then if you keep progressing forward a little more, you get something like this. All right, why did I not draw these out as the respective ions?
Because it's a solid.
It's a solid. It's thermodynamically more stable to be together than it is to be apart. Therefore, keep the solid a solid. Don't break that apart. We're going to call this a precipitate. I think that word showed up yesterday. So if you want to classify this as a precipitation reaction, something that forms a solid compound, that would be appropriate to do as well. Okay, net ionic. In general chemistry, honors chem 1, I think your teacher would have called these spectator ions. So find what are the spectator ions. If you go to a baseball game, you sit in the stands and you leave, unchanged, right? Like physically unchanged. The baseball players show up and they're physically changed in the reaction somehow, right? Blood, guts, tears, whatever. Well, something's coming out of them in that moment, but you're not. So if iron shows up the same way in both sides of the reaction, it's unchanged. Is it a catalyst? No. It's there. It's not participating in the reaction. It's just sitting there in solution, changing the dynamics of the solution, but not itself changing the reaction. What about sulfate? Is it unchanged? Silver?
That has changed.
What I mean by that is this shows up as an ion, independent of anything else, and now that ion shows up in a compound. Sulfate was changed.
So sulfate and sulfur are not spectator ions, but everything
Right.
else is.
Chlorates are. So you can see if it shows up the same way on both sides, it isn't. Whatever's left over, just draw down here.
And that's the net ion?
That's the net ionic. So the net ionic, in terms of words or an explanation, is what are the actual components that are participating in the reaction. Everything else is not. So this is way more efficient to draw here. And arguably for the rest of the year, we're really only doing the net ionic. We really never will do the total ionic. Rarely. Sometimes we balance the full equation if we need the math. So we really just care about what's actually going on in the solution. Okay, and if we were careful to carry down all of our coefficients, we should still have the same numbers of each type of ion on both sides, right? Well, that's your net ionic equation. The only subtle difference is if this came out to be aqueous, would you have a net ionic equation?
No.
No.
No, so you would just say no reaction. Nothing participates in the reaction. Okay? All right, let's do some balancing.
No, I think break.
Yeah, sounds like a break to me. I take Joanne.
Candy?
Go.
Candy?
Joanne
No,
is boss.
no.
Candy?
I've learned that since elementary school. Joanne's boss, and she says break
Oh,
is break.
God. Mac, I'm so sorry.
Did you just
That was-
bonk her in the head?
No,
Red
the
water bottle.
water ball stopped it.
Joanne,
Don't do that. I think he's
Sorry.
taking-
Joanne,